video, we are going to solve exercise 6 from worksheet 2. So let me read the statement of the exercise. So we have f is a non-constant holomorphic function in a disk around z0. And we know that this function is 0 at z0. And then we consider now the function 1 over fz. So g, or maybe let's call this h of z is equal to 1 over f of z. So this function has a singularity at z0, since f of z0 is equal to 0. And we know that the singularity is isolated because a holomorphic function has only isolated zeros. So the singularity is isolated because f has isolated zeros, since it is non-constant, So you always have the case of a function which is constant equal to 0, but we are assuming here that the function is not constant. So then this singularity is isolated. What we want to do is we want to show that this is a pole singularity. And we want also to find the order of this pole, giving a formula involving the derivative of f at the point z0. So why these derivatives come into play? Because they appear in the power series expansion of f. So let's write this power series expansion. So the power series expansion of f at z0 is given by f of z equal to the sum for k going from 0 to plus infinity of the derivative of f of order k at z0 divided by k factorial times z minus z0 to the k. So this we know, and now we can consider the smallest k such that the derivative of order k at z0 is different from 0. So let k0 be the smallest k such that fk of z0 is different from 0. Also, this number here, k0, will be some number bigger or equal than 1. And notice that this number exists because if all the coefficients, all the derivatives of f are 0, then all the coefficients in the power series are 0. And then we find once again that f is constant, which we know that it's not true. So maybe we can write this here. It exists because not all coefficients in the power series expansion are 0. So otherwise, f constant. Okay, so this means that we can write f of z as this first non-zero coefficient. So this f k0 z0 divided by k0 factorial times z minus z0 to the k0. And then we have terms which are of higher order in z minus z0. And we write these higher order terms simply by small o of z minus z0 to the k0. So this means that these terms here have higher powers in z minus z0. So we can factor z minus z0 out of this formula, and we find z minus z0 to the k0 times the first coefficient plus now terms which are of order bigger than 0. Okay, so now we have this expression for f. And we see we can use this to also have an expression for 1 over f. So this means that 1 over f of z, this was our function h of z. This is now given by 1 over z minus z0 the k0 times f of k0 divided by k0 factorial plus terms of order at least 1. So these are terms of order bigger than 0, so terms of order at least 1. So now this suggests, you see that this function should have a pole of order k0. Why is that so? Because now if we take the limit for z going to z0 of z minus z0 to the k0 times the function 1 over f, now you see we have this simplification, and we get now the limit of 1 over some function. But this function here below tends to f k0 z0 over k0 factorial when z goes to z0. This now is equal to 1 over f k0 z0 over k0 factorial plus 0. Maybe we can write here, since the limit as z goes to z0 of these remainder terms is equal to 0, because these have all positive powers of z minus z0. Okay, so now here we find a non-zero number. So this number here now is non-zero. This is different from 0. And so we know that this means that the function 1 over f has a pole of order k0. So since the limit or maybe better, since k0 factorial divided by fk0 z0 is different from 0, the function 1 over fz has a pole of order K0. So this gives us an example, an example of a way of how we can compute the order of a pole. So before going to the second part of the exercise, maybe we can write down an example where we show how we can use this theorem. So, for instance, example. For instance, let's take sinus f of z equal to sinus of z squared defined on small disk around 0. Then you see f of 0 is equal to 0. And we want to now compute the K0 in this case. So we start, so we know that f prime of z is equal to 2z times cosinus of z squared. And so f prime of 0 is again 0. Now we can take second derivative. This is product rule, 2 times the cosinus of z squared plus 2z times the derivative of cosinus of z squared. So I don't compute this derivative because now when I see what happens at 0, then I get 2 times cosinus of 0 plus 2 times 0 times this derivative. And now all this is equal to 0. So we get 2 times 1, this is 2. So this is now different from 0. So this implies that K0 is equal to 2 in this case, which means that 1 over sinus of z squared has a pole of order 2 at z0 equal to 0. Okay, so this gives us a way to compute the order of poles. I want also to make a remark here that you can have a similar result if you consider the power series expansion of sinus of z squared. So, alternative way to compute order of the pole, not using this the criterion above. Also, this is simply now writing the power series expansion of sinus of z squared. So you know that this is now z squared minus z squared cube over 6 factorial plus z squared to 3 factorial, 5 factorial, and so on. So you see here, you get 1 over z squared, then 1, and then all the other terms will be of order bigger than 0. Because this first term here is z to the 6. This other term here is z to the 10th. Okay, so if I factor out z squared, then all these terms will be z to the 4th, z to the 8th, so all of order bigger than 0. And so here again, we see that we have a pole of order 2. So this implies now that limit z goes to 0 of z squared times 1 over z squared 1 plus O z0 is equal to 1, different from 0, and then the pole of order 2. Okay, so just wanted to give always this alternative way using power series expansion, since it's always very useful. So let's go back then to our exercise. So we proved then the first part. So this part 1, now it's proved. And then now for the second part, we want to prove something a bit more general. So in this case, we have the quotient of G and F, where F is again a function which is non-constant and with a 0 at Z0. And then we want to understand when the singularity is removable and when it's not removable, how we can determine the order of the pole. And again, the hint is to look at the derivatives of G at the point Z0. So let's do this then. So let's go on and prove the second part of the exercise. So let now h of z equal to g of z divided by f of z, with f z0 equal to 0, f not constant. And again, here we have basically two cases. So I think here G is not required to be, right, in this case G is not required to be non-constant. So maybe we can already exclude the trivial case in which G is equal to 0. So if G is constantly equal to 0, then h of z is also equal to 0, and this means that the singularity is removable. So z0 is a removable singularity. So now if G is not identically 0, then I can write the Taylor expansion at Z0. So this will be also here h going from 0 to plus infinity of G h Z0 divided by h factorial Z minus Z0 to the h. And now I can define the smallest, let h0 be the smallest integer such that the derivative of G of order h, smallest integer h, such that gh of z0 is different from 0. Okay, so this exists, h0 exists since G is not identically 0. Okay, so once again, we find that G of Z can be written by isolating first Z minus Z0 to the H0 times GH0 of z0 divided by h0 factorial plus some terms which are of order bigger than 0. Okay, so now we have this g and use with the expression for f in the quotient. So this is g z f z. So this is now z minus z0 to the h0 g h0 z0 over h0 factorial. And below we get the same f. So we see that we can put the two powers of z minus z0 together, this one and this one. And we can rewrite this as z minus z0 to the h0, or better, maybe let's put them at the denominator. Let's put this as 1 over z minus z0 to the k0 minus h0. And here we have again these two terms. Okay, so now from this we see easily what is the nature of the singularity. So you see that if k0 minus h0 is 0 or negative, then the singularity will be removable. So if k0 is less or equal than h0, then the singularity is removable. Because now you can take the limit as z goes to z0 of h of z. And now this will be z minus z0 to the, so we have here maybe two cases, or let's do it maybe better like this. Let's check this z minus z0 times h of z. So this now is the limit of what? Of z minus z0 to the h0 minus k0 plus 1 times all these other terms. Plus, say below. And you see now this is positive. This number here now is positive. And therefore, the limit will be 0. So this limit is then 0 times this number here, G80 at Z0 divided by H0. And here you have F of K0 Z0 divided by K0 factorial. But anyway, this number is 0. So this means the singularity is removable. Instead, in the other case, so if K0 is bigger than H0, then Z0 is a pole of order K0 minus H0. Why is that so? It's enough to compute the limit of Z minus Z0 to the K0 minus H0 times the function Hz, which we saw this is Z minus Z0 to the K0 minus H0. And here come these other terms. And you see that this limit now is different from 0. It's G H0 Z0 times K0 factorial divided by F K0 Z0 H0 factorial. No? So this is different from 0, and this implies Z0 pole of order K0 minus H0. Okay, so this finishes the exercise. Maybe we can give also here an example of application of this criterion. So in this case, let me consider h of z equal to e to the z minus 1 divided by sinus of z cube. So now g of z is e to the z minus 1, and f of z is sinus of z cube. So what are now the H0 and K0? So we start with H0, so G. So let's see here for H0. We have to start computing G0. And this is e to the 0 minus 1, this is 0. So this implies H0 is bigger than 0. H0 bigger than 0. Then what is the first derivative? G prime of z is equal to e to the z, which implies that G prime of 0 is equal to 1. And this implies that H0 then is equal to 1. So now we can do the same thing for K0. But here, instead of computing just the derivative, we can once again maybe go a bit faster and write the Taylor series expansion. So this is sinus of z cube. And this again is z cube minus z cube 3 factorial plus other terms. So you see here the first term, which appears with a non-zero coefficient, is z cube. So this implies that f of 0 equal to f prime of 0 equal to f second of 0. They are all 0. And the third derivative is different from 0. No, actually, the third derivative is equal to 3 factorial equal to 6. Okay, so this implies that K0 is equal to 3. So we have now H0 is equal to 1, K0 is equal to 3. So this implies that the function Hz has a pole of order 3 minus 1, so equal to 2, at z equal to 0. Okay, so this finishes the application of this exercise.